Section R.3 is about exponents, roots, and order of operations. So an exponent is a whole number that indicates how many times a base number is to be used as a factor. So what I like to say is that mathematicians are lazy. If I was going to take 5 times itself 3 times, instead of writing that as 5 times 5 times 5, which takes a while to write out, I can write that as 5 to the third power, meaning I want to take 5 times itself 3 times. So here's our formal definition of exponents. If n is any positive integer and a is any real number, the nth power of a is written using exponential notation as follows. A to the n equals a times dot 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 a, where the number of times a's occurs is n. So for example, I've got 8 cubed. 8 is our base number, 3 is our exponent, and it means I take 8 times itself 3 times. So when I have an exponent of 2 or 3, those have a special name. I say 9 squared, 2 cubed. That comes from how we find the area of a square and the volume of a cube, right? Area of a square would be side times side. Volume of a cube is side, side, side. So side cubed is, or area is side squared. So that's where 9 squared into 2 cubed would come from. I can also have 5 to the first power. Well, 5 to the first power, that's just 5 times itself 5 times, which is 5. 3 to the fourth power, so 3 times itself 4 times, and 9 to the 0 power. Well, what does that mean? I'm going to explain that in just a second. Let's go ahead and write the following as exponents. If I have 4 times 4 times 4 times 4 times 4, right? So I've got 1, 2, 3, 4, 5, 6, 7, 8. So this would be 4 to the 8th. If I have negative 3 times 1, 2, 3, 4, that would be negative 3 to the 4th. If I've got y to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that'd be y to the 10th. Here I've got 3 7s. So I've got 7 cubed, and that's times some variable. 1, 2, 3, 4, 5. 7 cubed x to the 5th. Any number other than 0 raised to the power of 0 is 1. So a to the 0 is 1. Earlier I had 9 to the 0 power. That would be 1. Now, any number that doesn't equal 0 and is raised to the first power is also itself. So 9 to the first would be 9, x to the first would be x. That means I'm just taking 9 times itself 1 time. So 6 to the 0 would be 1, 5 to the 0 would be 1, plus 12 to the 0 would be 1, which gives us 2. So that's how we work with exponents of 0 and 1. Exponents of 0 really don't come up that often, but exponents of 1 would be a good thing to keep in your mind. So we previously looked at exponents, right? Exponents are used to square a number. Now we're going to take a look at square roots, which take us from a square number back to the number itself. So if I have 3 squared is 9, the square root, that's what this symbol is, it's a radical symbol. The square root of 9 is 3. So if we want to take 5 squared, we would take 5 times 5, which is 5 squared and gives us 25. Now, what if we're interested in going back to the number we squared in order to get 25? Well, since 5 squared is 25, we say 5 is the square root of 25, or 5 is the square root of 25 if we wanted to write it mathematically. In this notation, we call this symbol a radical sign. What's under the symbol is the radicand. So in this case, 25 was the radicand. And the entire thing altogether is a radical. Now, every positive number has 2 square roots. For example, negative 5 times negative 5 is 25. So the square root of 25 could be negative 5. And 5 times 5 is 25. So the square root of 25 could be a positive 5. We call the positive root the principal root. So if I was just to say the square root of 16, I'm always going to want that positive square root, which is 4. The square root of 4, 2. We want the principal positive square root. If we want a negative root, we're going to write a negative in front of the radical symbol. That tells me to simplify the radical first and keep the negative with us, kind of like we did for absolute values in section 1. So if I wanted the negative square root of 9, that would be negative 3. The negative square root of 64, that would be negative 8. And it's always nice, and I don't think I listed it, to know the first few squares. So the first few perfect squares are 1, because 1 squared is 1, 4, because 2 squared is 4, 9, 16, 25, 36, 49, 64, 81, and 100. So those are the first few perfect squares, and they're always good to just kind of know, especially as we get into deeper concepts throughout this text. Being able to identify a square can be very helpful. It's important to note that the square root of 0 is 0. It only has one square root. It's its only square root, and it's its own square root. So, good to know. So the square root of 16, for example, is 4. The square root of 81 would be a negative, the negative square root of 81 would be negative 9. And the square root of negative 4 at this moment in time does not exist. This is a complex number. At this point in time in this class, we're dealing with the real number line. So that means no negative square roots. That won't always be the case, but for now, no negative square roots. Now, it's important to note that not all square roots are going to be this perfect, nice number. Well, that's because not every number is a perfect square. Yeah, 1, 4, and 9 are, but what about 5? What about 3? So the square root of any number that's not a perfect square, that's where we get our irrational numbers are. And if you plug them into your calculator, you'll see that like they go on and on and on forever. They give you like 10 decimals. These are irrational numbers. They can't be written as a fraction. They're also called non-terminating decimals. So like, remember pi? We've talked about pi. Pi goes on and on and on forever, and there's competitions to see how many digits of pi you can memorize. Well, that's an example of a non-terminating, maybe not a number, because it has non-terminating decimals. They go on and on forever, and they don't repeat themselves.